Hmm. Okay. All right. Good afternoon. Good evening to some of you. My name is Christopher Gutierrez, and today I will present natural ventilation. I will cover the physical mechanisms, the design strategies, the limits, and several real case studies. The goal is to show how natural ventilation reduces cooling demand when design and climate support it. Before I go into the structure of the presentation, I want to give a quick background on what natural ventilation is. So natural ventilation uses wind and buoyancy to move air through a building. It reduces mechanical cooling demand and improves indoor air quality by bringing in outdoor air. The process depends on building geometry, opening placement, and climate conditions. When these elements line up well, natural ventilation becomes a stable, low energy strategy. So why does this matter? Cooling loads take a large share of building energy use. So HVAC systems are responsible for most of the operating costs in many climates. Natural ventilation lowers energy use and cuts carbon emissions. It also improves indoor pollutant dilution by increasing outdoor air exchange. As energy prices rise and comfort requirements grow, reducing mechanical cooling loads becomes more important. Natural ventilation supports that when applied correctly. Now that we have the basic idea defined, I will outline the objectives of this presentation. Here are the objectives of the presentation. I'll explain wind-driven and buoyancy-driven ventilation. I will identify the key design strategies. I will show how climate affects performance. I will review the main limits and constraints. I will present real case studies, and I will highlight why natural ventilation supports low energy building design. So starting with wind-driven ventilation occurs when external wind creates pressure differences across the building facade. The windward side receives higher pressure and the leeward side receives lower pressure. So air moves through the interior from one side to the other. Cross ventilation is the most effective because openings align directly with the wind. Single-sided ventilation works only in small or shallow rooms since it depends on turbulence. Wind towers capture higher elevation airflow and direct it inside. Building orientation controls how strong this airflow becomes. Okay. Now regarding buoyancy-driven ventilation, buoyancy-driven ventilation relies on temperature differences. Warm indoor air rises and exits through higher openings, as you can see in the diagram to the right. Cooler outdoor air enters through low openings to replace it, also seen on our diagram. This creates a vertical airflow known as the stack effect. The effect becomes stronger in tall spaces because the temperature difference creates more upward force. Solar chimneys heat air inside a vertical shaft to increase upward flow. Atriums act as large exhaust volumes. This method works best when the building has a clear height difference. Moving on to key design strategies. So design controls how effective natural ventilation will be. Large operable windows increase airflow. Openings should align with the prevailing wind direction. Interior layouts need open paths so air can pass through without obstruction. Narrow floor plans improve cross ventilation because they reduce the distance air must travel. Shading reduces heat gain and helps maintain comfort. Thermal mass stabilizes indoor temperature during warm periods. These strategies improve reliability and comfort. So now let's talk about climate-based strategies. So natural ventilation performance depends on climate. Hot, arid regions use shading courtyards and wind towers to reduce heat gain. Hot, humid regions require large openings and high ventilation rates to move moisture out. Temperature climates, temperate climates use natural ventilation during mild seasons. Cold climates limit natural ventilation to avoid heat loss. Hybrid systems provide stability when wind or temperature conditions are weak. Each climate zone requires a different design approach. Some challenges and limitations. So natural ventilation has real limits. It depends on weather, so airflow can drop during low wind or extreme temperatures. Noise from outside reduces comfort in dense areas. Outdoor pollutants enter through open windows. Security concerns restrict how much windows can remain open, especially at night. And high-rise buildings experience uneven pressure across the facade, which makes natural ventilation harder to control. Occupant behavior also affects results because people do not always operate windows in a consistent way, and you can't have the whole building using it the same way. And now let's move on to some case studies and applications. So several buildings show how natural ventilation works in real applications. As you can see in the picture to the right, that's the Commerzbank Tower, which uses an atrium and sky gardens to move air vertically. And we also have the WindowMaster headquarters, not shown here, but it uses automated windows with CO2 and temperature sensors. Also, classrooms at the University of Hartford use cross ventilation to reduce cooling loads. Traditional wind towers in the Middle East capture airflow at higher elevations. The Bedzed Eco Village uses natural ventilation with passive cooling for residential housing. Schools in Singapore use large openings and shading to handle humid conditions. These examples show the method works across many climates and building types. Okay, and now conclusions. Natural ventilation reduces cooling energy use when design and climate align. It works through wind and buoyancy, like we spoke about earlier. And climate has a major influence on performance. Hybrid systems improve reliability when natural forces are weak. Real projects show strong results in schools, offices, towers, and housing. Natural ventilation remains a practical, low energy option when applied carefully. Here we have some of the references I used to formulate this presentation. And that pretty much wraps up the presentation. Thank you guys for listening.